1. Rubber compound testing. A. Specific gravity. The specific gravity of a rubber compound refers to its density. This is a measure of the mass of the rubber divided by its volume. The units therefore are typically quoted as grams per cubic centimetre, G/cc. This merely indicates the weight of the rubber and is useful to identify the purity of the compound. For example, a natural rubber compound has a specific gravity typically of 1 gram per cubic centimetre or less. Neoprene may be 1.5 grams per cubic centimetre. B. Hardness. The hardness of a rubber compound, when suitably formulated, will determine its ability to withstand impact. It is measured using a durometer. The scale used is called Shore-A, whereby the lower the number, the softer the compound. The recorded result is usually specified to have a plus or minus tolerance, since the reading will vary across the surface of the product. In applications of high impact areas, it is desirable to have 60 Shore-A hardness, whereas in applications such as rubber lining, it is common to use 40 Shore-A. C. Elongation at break. The term elongation is used to describe the ability of rubber to stretch. Elongation at break refers to the maximum that a section of rubber will stretch at which it breaks. Its value at point of break is expressed as a percentage of the original length. Compounds of natural rubber normally have very high elongation, typically between 450% to 700%. Unless the desired application requires the rubber to be stretched during service, then elongation of the rubber is not particularly significant. In rubber lining, for example, the rubber is bonded to steel, therefore the elongation property of the rubber is largely irrelevant. Likewise, for conveyor belting, the fabric or steel reinforcing will determine the ultimate elongation. D. Tensile strength. The strength of a rubber compound is measured in megapascals, MPa. It is the force in newtons being applied when the rubber snaps, divided by the cross-sectional area to give the tensile strength. The higher the number, the stronger the rubber. The tensile strength of the rubber is closely related to the rubber's resistance to cutting and gouging by sharp objects. Belting with rubber covers of high tensile strength are often quoted as being M24 or M20, whereby M signifies it is a compound based on natural rubber, and 24 or 20 denotes the tensile strength of the rubber in megapascals. E. Abrasion resistance. The abrasion resistance of rubber is measured by taking a round plug sample and passing it over a rotating abrasive drum. The volume of the rubber sample is measured at the beginning and end of the test. The difference in the rubber volumes is called the amount of rubber loss, measured in cubic millimetres. The lower the number, the more resistant the rubber is to abrasion. It is desirable to have a lower abrasion loss reading, particularly where the rubber is in high abrasive applications. Highly abrasion-resistant compounds will have results below 100 millimetres cubed. It is important to note that the arm holding the rubber plug can weigh 5 or 10 newtons, and this should be quoted when the test result is given. The typical test is conducted in dry conditions, and a separate test method is employed for wet abrasion testing. F. Aging test. The speed at which a rubber ages is determined by subjecting some samples to a heating oven at 120 degrees Celsius for periods of 24 or 48 hours. The test can measure the changes in physical properties of elongation, tensile strength and hardness of the rubber from the beginning and the end of the test. The change in these physical properties are recorded as a percentage, and the higher the value, the more susceptible the rubber compound is to aging. This testing may be of particular significance to rubber, which is exposed to the elements in extreme heat conditions for long periods of time. It does not, however, take into consideration UV, ozone, or other degrading factors. 2. Fabric conveyor belt testing. A. Tensile strength. The tensile strength of a conveyor belt is generally measured in newtons per millimetre, N per mm, or kilonewtons per metre, Kn per m. The test is conducted by fixing a sample of the conveyor belt into a tensile tester and applying a force until the belt snaps. A conveyor belt specification of 800 by 4 indicates the belt has a minimum tensile strength of 800 kilonewtons per metre of belt width for the total of 4 plies. If a belt is manufactured poorly, not all plies may be evenly tensioned, and therefore the total belt strength could drop significantly below the combined strength of all the plies. This test is therefore a good indicator of belt quality. B. Adhesion test. The adhesive strength of fabric-reinforced conveyor belts is measured in newtons per millimetre, N per mm of width. The test is conducted by cutting a sample and then pulling it apart using a tensile tester. This measures the average force used to pull the belt apart, giving an indication of how well the conveyor belt has bonded together. Poor adhesion levels may result in delamination of the conveyor belt during service. The adhesion is tested between the plies and between the cover and plies. C. Electrical resistance. The electrical resistance of a conveyor belt is measured in ohms or megaohms. This is a measure of how much the rubber will resist electrical current. Low resistance means the rubber is a good conductor and therefore will not allow charge or sparks to develop, making it suitable for underground mining. High resistance means the rubber is a poor conductor and therefore can be used in electrical applications to insulate against electric shock. In the case of underground coal mining, the limits are set by Australian standard AS 4606, which states the belt must not have an electrical resistance greater than 300 megaohms. D. Tear strength. The tear strength of a conveyor belt is quoted in kilonewtons, kN, which measures the force required to rip the belt apart. A rectangular sample of the conveyor belt has a slice cut in the bottom, creating 2 flaps which are then pulled apart in a tensile testing machine. The rip resistance of a conveyor belt can be an important factor in determining the suitability of a belt for various applications where ripping can be a problem. The resistance to rip propagation in fabric belting will depend on a number of factors, such as the fabric polymers used, the amount of yarn used, and the type of weave pattern. The rip resistance can be tested along the length of the belt, the warp, or across the width, the weft. E. Flame resistance. The ability of a conveyor belt to resist burning is tested using a flame testing apparatus, and it measures the amount of time in seconds that a sample piece of belt continues to burn after having been exposed to a standard flame. It also records the amount of time a belt sample continues to glow once the flame has been removed. The flame resistance requirement for belts used underground in coal mining applications is governed by Australian standard AS 4606. F. Drum friction testing. The ability of a conveyor belt to resist burning and sparking as a result of being stuck on a conveyor system where the belt is not moving but the drive pulley continues operating can be measured using a simulation on a drum friction testing machine. In this case, the temperature of the belt is recorded over a period of time as the pulley continues to rub on the belt. Therefore, the units recorded are degrees Celsius. Depending on the standards used, the temperature is not allowed to go above a certain set limit. In the case of AS 4606, the maximum temperature allowed is 325 degrees Celsius. Testing is usually conducted on the top cover and then also on the bottom cover. In addition, the testing is conducted once using a jet to blow compressed air onto a belt to simulate a draft which may be present in mining shafts. Therefore, testing is specified as being with or without air. G. Gallery test. To determine how much a flame will propagate along a belt once it has caught fire can be determined using a gallery test apparatus. The results of this test are determined by measuring the amount of sample belting left undamaged once it has been removed from the flame, and therefore this is in units of millimetres. The requirement, as per AS 4606 standard, is that there should be no less than 250 millimetres of a 2-metre belt sample left undamaged as a result of the burn test. The intent of this test is to determine the ability of the belt to resist burning in a confined tunnel situation, as is typical in underground mining applications, which are susceptible to hazardous conditions, such as exposure to methane gas, as in coal mining applications. H. Troughability. The ability of a conveyor belt to form a trough is measured by a device called a troughability tester. The troughability ratio, or factor, is expressed as a ratio of the amount a belt deflects when in free suspension, divided by the width of the belt in the flat position. This determines the stiffness of a conveyor belt, and therefore its suitability to carry a particular load over a specifically designed system. Problems can result if the belt is not of correct troughability. If the belt is too stiff, material can spill over and the belt will wear unevenly. If the belt is not sufficiently stiff, it could fall between the idler rollers and result in pinching and delamination. 3. Steel cord belt testing. A. Steel cord adhesion test. The bond strength between the rubber and steel cords in a conveyor belt is measured on a tensile tester in newtons and is the force required to pull a steel cord out of the rubber. This is an important measure to determine the integrity of the bond between the steel cords and the rubber covers. The higher the bond strength, the greater the likelihood of long service life. In addition to this static test, the dynamic bond strength can also be tested, whereby tension will be cycled over a long period of time. This gives an indication of the expected changes in performance over a given duration of time. 4. Free testing. When comparing rubber lining or conveyor belts, it becomes clear that different companies use different tests, testing standards or units. This makes the job of comparing one rubber product against another confusing and often impossible based purely on data sheets. Whether determining suitability of rubber for lining applications or conveyor belting for specific systems, or whether simply comparing one product against another, the chemists at All Rubber can help. Our testing laboratory located in Perth can perform most routine physical testing. All Rubber offers free testing to clients who are invited to view the tests and compare products currently being used with no obligation. The most effective way to compare rubber products is through side-by-side testing on the same equipment and utilising the same test procedure. Our chemists will be happy to assist in recommending or developing products, particularly for problem areas, helping to achieve better wear life, heavier throughput, lower maintenance costs, and more efficient running costs. A free service from All Rubber designed to maximise profits and returns for the end user, you.